Well, hello, Blake and Daniel. Looks like we're ready to go here with another time looking at 7.2. Just to let you guys know, I don't have your tests graded, but I hope to have them done by the end of today. So hopefully I'll have them done by the end of today, and I can post them before tonight online. We'll see. At the very least, I'll have them done tomorrow. So let's look at 17.2, one more day in 17.2, Stokes' theorem. So the truth is, Stokes' theorem is one of those things that it's not like some theorems where it's like, wow, this is really going to save us a lot of time and effort. The truth is, a lot of times, it's not any easier than just directly evaluating the integral. But in certain circumstances, it can be a real advantage. So let's go ahead, let's take a look. Today, we're going to take a look at another example of two different ways to do it, using Stokes' theorem and not using Stokes' theorem. So let's look at 14. I picked a problem that was kind of a bear. It actually is going to take the entire piece of paper here for me to show you how to do this, because we're going to both do it without Stokes' theorem and then we're going to do it with Stokes' theorem. So the first thing it says on 14 is it does give us a vector field. So we have our vector field 0, negative z1. And then it says that S, our surface, is the spherical cap here. X squared plus y squared plus z squared is less than or equal to 1. And it's that spherical cap where z is greater than or equal to 1/2. So if you want to think of it, if z was greater than or equal to 0, then you'd have the hemisphere sticking up there above the xy plane going up to a z value of 1. But now we just have the little cap part there, because we start with the plane of z equal to 1/2 and then go above that and top off our hemisphere. So the book doesn't give a picture of it, but I think you can picture it pretty easily. I will break down part of it here, but I'm not going to try to draw a picture of the whole thing. Okay, so the first thing it asks us to do is it asks us to evaluate the double integral over the surface of our vector field ds. And it directly is just a surface integral. So in order to do that, we know that we want to evaluate this. What we have to do in this situation is we are going to do a double integral, which means that we have to go ahead and we have to parameterize the surface with two variables. And then we have to, in order to do our dot product here, we have to get our normal vector there as far as that goes. So doing this, the first thing we have to do is we have to look at our parameterization. And here's where I kind of sketched a little bit of what's going on, because we know since we're talking about part of a sphere, we're going to use spherical coordinates. But the question becomes, what are the limits going to be on theta and on phi? Fortunately, we have a radius of our sphere of 1, so that's a constant. So we really only have to look at the two variables of theta and phi. And if we see here, notice what we've got is I've kind of drawn this in here. This would be the z. And if I want to think of it, I guess I could kind of try to sketch in the entire cap piece as it kind of comes like that. Kind of comes down like that as it goes around. So it's this cap piece here. And this is probably not very good because it makes it almost look like it's touching that axis, but it's not. It's a very flat piece, kind of like that. Anyway, as it goes around, I know that it starts here with the z value here of 1/2. Z's got to be greater than 1/2. So it's just this top part right here, just this shaded part right up in there like that. And so with this, where it's going to be 1/2, notice I've got to find the angle of phi. Remember, phi starts here with the positive z and goes down here. So where this is 1/2, we know that this measurement right here would be radical 3/2. So the measurement that would produce that is where this is pi over 3. So I know that my theta will go from 0 to pi over 2. It'll be the whole circle. And my phi will go from 0 to pi over 3. So with that, I can go ahead and I can parameterize my surface. So this is my surface parameterized in terms of theta and phi. So I know, and I'm just using, this is just, you should be familiar here, spherical coordinates. cosine theta, sine phi, sine theta, sine phi, cosine phi. There's my parameterization. Now, next step. Now, the truth is, I wrote this out, but you probably, this is a parameterization that comes up enough that probably you should memorize or at least be pretty good at figuring out what the normal vector for this is, because we've done it numerous times. I'm going to go through the process again just to remind you, but you'll see that it's what we've gotten before. First, I have to take the partial. So remember, if you remember what I have to do, that normal vector is going to be the partial with respect to theta, crossed with the partial with respect to phi, will be our normal. So our partial with respect to theta, pretty straightforward there. Our partial with respect to phi, we have our cosine theta, sine theta. I did that wrong. That's a phi. I wrote a theta. That's a phi there. Catching my mistakes. And then sine theta, cosine phi, negative sine phi. Now we cross product. Now when I do the cross product here on these, I'm going to do that, and I can do that without, I think, and you guys are probably getting to this point too, where we don't have to write out the matrix all the time. We can look at it, especially when we write this one over this one like this. To get our x component, we can just cover this up, and we can quickly cross multiply and see I've got negative cosine theta, sine squared phi, minus 0, so we get our value there. And then getting our y component covering up here, I see that I've got a positive sine theta, sine squared phi, but I'm subtracting that middle term, so it becomes negative. And then for my last term here, this is the one that's kind of messy because I've got double products there. So multiplying here, I've got negative sine theta squared, sine phi, cosine phi, and then subtracting, going across this way, I get cosine squared, sine phi, cosine phi. So simplifying this down, and here's the part where we get to something that should look pretty familiar. We can factor, notice this, if I factor out this negative sine phi, cosine phi, I just get sine squared plus cosine squared, so that's 1. So here, this just becomes a negative sine phi, cosine phi. So if I go ahead and factor out the sine of phi, I have a sine of phi in all of these things here. I end up with this, except that I end up with negatives in front of all of these. But once again, I have to decide whether or not I want it where it's positive or negative, which normal direction do I want. And it tells me, in this case, I've got an upward, I believe it says it's an upward pointing, where does it say the vector here? It says, well, I know we want an upward, I'm not sure where, but knowing in order to get an upward, here, someplace it says it, and I don't know whether it's, I can't see it real quick in the problem, but if I look there, I see that for this to be positive, z direction has to be positive if it's pointing upward. So I want the one where they're all multiplied through, change the signs of everything. So that done, now I have my normal. Now I can go ahead and integrate this directly. So my f dot ds is my vector field f parameterized, with the parameters there. And the dot ds becomes dotted with my normal vector. So that's going to become the double integral. And if I go ahead and I do this dot product here, notice what I get when I do it. I get 0 times this is just 0. So then I've got negative, and this becomes sine theta. And I do have to be careful here when I do my normal. I have to remember that I distribute this sine phi in. So this is sine theta sine squared phi times negative cosine phi, so that's a negative. There's my sine theta sine squared phi cosine phi. And then this is sine phi cosine phi. And if I go ahead and multiply by 1, I get that. Integrate. And you can go through the process of this integration. It's not too bad, but I don't really have room or the time to do it, so I'll let you know it is 3 pi over 4. All right, now let's evaluate the double integral, the surface integral with Stokes' theorem. So using Stokes' theorem, the whole idea of Stokes' theorem is taking a double integral and turning it into a single integral. That's the whole idea behind it, a line integral as opposed to a surface integral. Because oftentimes the integration is easier that way. So they do tell us this, and if they didn't, we would have a much tougher time doing this problem. But they do mention to us that the curl of A is, I should say, we know that F is equal to the curl of A, but we wouldn't know what A is if they don't designate to us. They designate that A is actually this vector 0, x, xz, but they want us to verify that really, that this really does give us F if we take the curl of this. So let's verify that. So for F, the first component of F, the F1, the x component of F would be, remember, that's where I take the derivative of the y with respect to, so I don't take a derivative of the x component to get the x component. I take a derivative of the other two. So I take a derivative of, in this case, I'll start off, because I have to take a derivative with respect to y of this and z of this. So I do the one with y first. So that becomes derivative of this with respect to y, which is just 0. And then, so that's that. Did I say that right? 0. This with respect to y, which is going to be 0. And the derivative of this with respect to z, which is also going to be 0. So I get 0 minus 0, which is, whoops, which is not that, but my x component of my vector. Remember, this is what my f is, so it needs to be 0 here. This one right here is what we're looking at. So my y component. So for my y component, I won't look at this here. So I'll take the derivative of this with respect to z and the derivative of this with respect to x. But since I subtract the middle one as I do this, I actually have to go to do this one, this one first with respect to z. So I've got derivative of the a1 term with respect to z, the derivative of the a3 term with respect to x. This is 0 minus this is z, so I get negative z, which is what I got in my middle. If you scroll down there and you look for your vector field f. And then finally, f of 3, getting the component here, so I'll cover this up, but I know I need to take this with respect to x, this with respect to y, and I get 1 minus 0 for 1. So it does verify that when A is this, yes, it is true that the curl of A does equal our vector field 0, negative z1. So we verified that. So with that in mind, what then it asks us to do is it asks us to use Stokes' theorem to evaluate the surface integral. So Stokes' theorem basically says that this double integral is equal to the double integral of the curl of A dotted with ds, which is just the single integral of A dotted with ds. So working this, the curve that we have to worry about is just the boundary curve. So in this case, the boundary curve, if you remember, that is that bottom rim of that part of the sphere, that spherical cap that we have there. Well, I know that when we are at a z value of 1/2, we already talked about that I would be radical 3 over 2 out in the other direction. So I'd have a radius of basically radical 3 over 2. So I got a circle, and it's in a plane parallel to the xy plane. And it's going to be x squared plus y squared equals, and when I square that radical 3 over 2, I get 3/4. And I'm in the plane z equal to 1/2, okay, parallel to the xy plane. So now I have my boundary curve. Now what I have to do in order to do this, I have to parameterize my boundary curve. So parameterizing that boundary curve with the formula that we call gamma of t. So this is just parameterizing this surface here. If I go ahead and do that, sorry, not surface, but boundary curve. Okay, produces an individual curve there. And then what I need to do when I go to do this, doing this a dot ds, is I must take my vector a, and when it's parameterized with gamma, putting that in the appropriate spots here. If this is gamma, remember my vector for a was 0x xz. So there's 0, there is my x, and here is my x times z right here, which ends up being my x times the 1/2 there. So we get that. And then I have to take the derivative of the gamma. So taking the derivative of the gamma, I get this. So that means that a of gamma times the derivative of gamma, or I should say dotted with the derivative of gamma, is just 3/4 cosine squared t. So now I know I've got the line integral going from 0 to pi over 2 of 3/4 cosine squared t dt. And yes, we can use a power reducing identity there and go ahead and integrate. At this point, I'm running out of paper and time. I don't want the video to be too long, so I'll tell you it is 3/4, which was exactly what we got doing it directly. So is Stokes' theorem easier in this case? Well, maybe if they give you what the what A is in this case. Might not be so easy if you didn't have that. But either way, there are certain cases where Stokes' theorem becomes a real advantage, so you need to make sure that you can do it with Stokes' theorem or do it directly. Homework, 17.2, 11 through 17 odd. Okay, have at it, and we will be moving into 17.3 tomorrow.